right, let's continue with our notes. Page 29. Okay, we talked about how we know that the limits as we approach a vertical asymptote doesn't exist, but if it's a one-sided limit, we have to provide information in terms of where the graph is headed. We know that if your graph is approaching a vertical asymptote, it's either going up to positive or negative infinity, and we have to provide that additional information. So if it's a one-sided limit and it's a vertical asymptote, does not exist, is not going to be a good fit for that answer. We have to say either positive or negative infinity. And the way we did that was we played with decimals, right? We found a value that is relatively close to that asymptote. And if it's negative or positive value, then we know that's where the arrows are headed as we get closer towards that asymptote. Okay, so now we're going to be talking about limits at infinity and horizontal asymptotes. So before we're talking about what if we're approaching a vertical asymptote, it's going to go up to infinity. But then if we're approaching infinity, that's really end behavior. So we could have graphs that look like this, right? Where it's asking what is the limit as x approaches infinity, and then if the graph looks like this, then we'll just ask, where the graph is headed in terms of, as we follow that arrow, what is the y value getting closer towards? And we all know how to do this because we've seen it in terms of finding horizontal asymptotes. And the strategy there is we compare degrees between numerator and denominator. Okay. So if we see a limit as x approaches infinity or negative infinity, we switch gears in terms of our strategy. If it's approaching a real number, we always plug in that real number because we want to know what's happening. Is there a hole? Is there an asymptote? Is the graph continuous? But if we're approaching infinity, we're not going to plug in any numbers. We know that we're asking what is the behavior of the graph as it exits from view? Is it flattening out towards a number, or is it going up to positive or negative infinity? So we're just basically figuring out what's happening with those arrows.
Yeah, that's flipped over to this period.
Okay. I'll have you in C13. Okay, so here are the three scenarios. If the numerator degree is less than the denominator degree, then our horizontal asymptote is always equal to 0. So in this case, if I have limit as x approaches infinity, 3x squared minus 7 over 2x cubed plus 1, this is going to be equal to the 0. Okay. We can also reason this out without feeling like we have to memorize it, because if we think about this as, okay, if we're approaching infinity, that means we're increasing the numerator and denominator, and we can see that numerator is 3x squared minus 7, that's going to get larger and larger. 2x cubed is also getting larger and larger, but which side is growing faster as we approach infinity? Which is growing at a faster rate? Denominator, because the x cubed, right? Eventually that x cubed is going to overtake that x squared, even if that x squared with that 3 coefficient in front may have a higher starting point. But that 2x cubed is going to overtake it. And if your denominator is getting faster than your numerator, what's happening to your fraction? It's going to get smaller. And if we follow that idea, if it keeps getting smaller and smaller and smaller, eventually it's going to approach 0. Okay, so that's one way to think about it. Next, if my denominator and numerator degree are the same, then my asymptote is simply the coefficients divided by one another. So here, if I look at limit as x approaches infinity, I see x squared. They're both essentially moving at the same rate. It's just the ratio of the 5/2 is going to land that numerator a little bit higher than my denominator. But essentially, it's growing at the same rate. So it's going to hold steady at this line of y equals 5/2. I do want to point something out here that I see some students mess up with is, what if I did this? Limit as x approaches negative infinity of the same expression. Is that going to change anything? My ratio is still what? 5/2. That negative is not going to change my my horizontal asymptote. It's still going to remain 5/2. It doesn't matter if I'm going left or right. This graph is going to look maybe something like this, where that asymptote is holding steady at 5/2. It doesn't matter if I'm going left or right. It's the same asymptote. So I see some students see that negative. They feel like they got to do something different, and they end up changing the sign of the coefficients. So we don't do that. Okay? It's just the ratio of the coefficients, regardless of whether you're going positive or negative. Now, last option here. If the numerator degree is greater than my denominator degree, then there is no horizontal asymptote. There could be a slant asymptote, but we're not going to worry about that in this course, which is it's either horizontal asymptote or we don't have an asymptote. But the limit is either positive or negative infinity. If my numerator degree is lower than my, sorry, if my numerator degree is greater than my denominator degree. So in this case, if I do limit as x approaches infinity, we see the x cubed versus x squared. The x cubed is growing at a faster rate than x squared. That means this fraction is getting larger and larger and larger. It's either going up to positive infinity or it's going to get down to negative infinity. But it's going to be one of the infinities. Right? So the only thing we have to worry about is having to decide between these two options. And the way that we can easily do this without having to graph it or without having to look at a bunch of ordered pairs is let's just test a number in the direction that we're headed in. So here, I'm approaching positive infinity. So let's see what happens to the graph at around 100. That's just, for me, that's an easy large number for me to plug in. And if at 100, my graph is in the positives, that means it's steadily growing up. It's heading up. But at 100, if my graph is steadily in the negatives, then I know my graph is headed in this direction. Right. Again, we can do this without having to do a lot of messy calculation because all I care about is positives and negatives. So if I plug in 100 in for x, 2 times 100 cubed plus 1, is that positive or negative? Positive. If I do 7 times 100 squared plus 5 times 100 plus 10, that's also positive. So positive over positive is positive infinity. Now, if my numerator is a higher degree than my denominator, then my sign does matter. If I approach positive or negative infinity, that's going to influence the number I test. Because if I'm approaching negative infinity, that means I'm following the graph to the left. If I'm following the graph to the left, I need to know where it's headed. It's either, it could be still, we know it's going to be one of the infinities, but you're not going to know for sure unless you actually test it. So option 2 here, infinity, negative infinity has no impact on your limit. But if my numerator degree is higher than my denominator, then the direction that I'm headed, either positive or negative infinity, could have an impact on my on where my graph is pointing. Okay. Here's a side note here. Horizontal asymptote is a description of end behavior, but it is not a boundary that the graph cannot cross. Okay. So in other words, the horizontal asymptote is not a restriction for the graph. It is more a description of the end behavior. So sometimes you may see a graph that looks like this. Okay? Your graph is never going to cross the vertical asymptote. We know that. But it seems kind of strange for some students to see, wait, why is this graph able to cross the horizontal asymptote? And again, the reasoning is because the asymptote is really for the end behavior. It's really telling us how the graph is going to behave as it exits the graph. It's not really indicating that the graph can't cross it at some point. It's more of a description of the end behavior and not a restriction. Okay, so let's see if we can practice 4 through 9 and yeah, let's see how we do. And now we'll go over these problems once you guys try it. All these are approaching either positive or negative infinity, so you know you're going to compare degrees for each of them, and it's going to either fall with either category 1, 2, or 3. Okay, so number 4, my degree in the numerator is higher than my denominator. I'm approaching infinity. So I know that my overall fraction is getting larger and larger. I just now have to decide, is it getting larger towards positivity or is it getting larger towards negative infinity? So we choose a large number to test in the direction that we're headed. We're headed towards positive infinity. So I just like to choose 100 to test. You know, you can test a larger number or you can test another large number if you want. But to me, 100 is an easy number for me to target. And then I just care about the signs. I don't care about what the actual value is. Numerator is positive, denominator is positive, so positive infinity. Number 5, again, my numerator has a higher degree than my denominator. This time, though, I'm headed towards negative infinity, so I'm going to test negative 100 to follow the arrow as it exits to the left. And then here, negative 100 into the numerator is still positive, but a negative 100 into the denominator, I get a negative. So positive over negative is negative. Number 6, I find my highest degrees. Degree 1 in the numerator, degree 1 in the denominator. I take the ratio of the coefficients, so negative 3 over 2. And we don't want to let that negative infinity throw us off. We don't care about that negative infinity. We just care about the fact that if the degrees are the same, we're still going to take the ratio of the coefficients. We're not going to let that sign be changed because we're headed towards negative infinity. So to highlight that fact, if you look at number 6 and 7, one's going to positive infinity, the other's going to negative infinity. The ratio of the coefficients is the same, so my horizontal asymptote is holding steady. It does not change to a different number because we're going in a different direction. For 8, my denominator has a higher degree, so my fraction is getting smaller and smaller. So that value is getting closer towards 0. So that's where my horizontal asymptote is, y equals 0. And number 9, degree is higher in the numerator. So I'm going to test negative 100. Test the signs. I get a negative over a positive, so negative infinity. Okay. Any questions? All right, page 30. So this is kind of an exception to the rule. So this is kind of like a special case because this graph is a little bit strange. So let's talk about this graph, this function here, 3x minus 2 over the square root of 4x squared plus 5. If I were to ask you to compare degrees between numerator and denominator, what would you say? Numerator has degree what? 1. What's the denominator's degree? Also 1. Why is that? Yeah. Eventually that x squared is going to get canceled out with the square root. So when everything is said and done, the denominator is basically still degree 1. So the degrees basically match, which means that we're going to take the ratio of the coefficients. However, because there's a square root involved, that's going to throw things off a little bit in terms of how the graph looks. So here, technically the degree matches. And I'm basically going against what I just said before. I said for rational functions, it doesn't matter if we're going positive or negative infinity. If my degrees match, I'm going to get the same horizontal asymptote. But this is the one exception. This type of graph has a split asymptote. So one end is going towards one asymptote, but then the other direction is headed towards another asymptote. But the good thing is that these asymptotes are going to be the same ratios, just different signs. So if there's a 3/2 on one side, there's going to be guaranteed a negative 3/2 on the other side. So it'll just be asymptotes with the same ratio, just different signs. So whenever you see this type of function and there's asking for horizontal asymptote, we basically have to involve finding the limit in both directions. So we're going to evaluate approaching infinity and approaching negative infinity. So let me just go through one at a time with you. So if we're approaching infinity, we know that we're going to compare degrees. Degree 1, you said. Degree 1 also below, because the square root of x squared eventually turns into degree 1. And then we got to take the ratio of the coefficients, right? So numerator is 3. What's the denominator? 2, because that root is impacting the 4. Root 4 is 2. So there's a horizontal asymptote at y equals 3/2 as we approach infinity. And that is consistent with the graph that we see in front of us. Now, you're not going to see the graph. If you see a problem like this, you're not going to be able to have the graph in front of you, but I'm just wanting to show you the graph so that you can see the visual connection with the number that we're getting. Now, if we're approaching negative infinity, we're also going to compare degrees. And the degrees are still the same, right? Still 1, degree 1, and degree 1 below. But imagine what's happening, though, if I were to plug in like negative 100 or negative 200. My denominator is going to turn what? Negative, but my denominator will always stay what? Positive. So the fact that one side is always going to move in a different direction, or is always going to have its sign changed, and the denominator is not going to follow suit, there's always going to be that mismatch of signs. And that mismatch of signs is always going to force this to be a different sign than what we start off with. So that's why we're getting -3/2 or whatever the opposite sign of what we started with. So with a strange graph like this, we're going to have two horizontal asymptotes. And then so we'll say horizontal asymptotes then exist at y = 3/2 and y = -3/2. This is a very unique and special case, but it has shown up on previous AP exams, so just want to make sure I go over it with you. Typically, most graphs don't have split asymptote. This is a very unique case. Let's see. Last topic. Okay, last topic here. This is comparative growth rates. This is a very useful skill to apply, especially when we have different families of functions that are divided by one another. And then some of these limits may seem really difficult to handle, but ends up easier because of the clean relationships that can exist between these families of functions. So comparative growth rates indicates that families of functions grow at predictable rates in relation to each other only as x approaches infinity. So that's important. This relationship breaks down if we go left, but if we approach infinity, then we have these nice predictable behaviors between these graphs. So again, this only works if we're approaching infinity. Logs between the ones that we're going to look at is the one that grows slowest. Okay, so if you see a natural log of x or logs of other bases, all your log functions is growing, but it's growing at a pretty slow rate. It's rising, but it's rising very, very slowly. It's moving to the right faster than it is going up. So I'm going to just give an example here, natural log of x. Followed by radicals. Radical function also kind of has the same shape as natural log, but it grows at a slightly faster rate. Next up, polynomial. Now, if we're really close to 1, then it doesn't seem like one is growing faster than the other, but then it's only as we go further to the right, we're really going to see the distinction between the pace of these graphs. Next up is polynomial. Algebraic equation could be x cubed, x to the fourth, even x to the first power. Anything that's algebraic is going to grow at the next fastest rate. And finally, exponential, like e to the x, 2 to the x, 3 to the x. This is going to grow at the fastest rate. So the nice thing about these relationships is we just have to discover which one is faster and slower, and we should be able to come to a nice, clean conclusion. Because if my denominator is growing faster than my numerator, what's going to happen to my fraction as I approach infinity? Approaches what? 0, right? It's going to get smaller and smaller, and so eventually it's going to head towards 0. Likewise, if my faster function is above and my slower is below, then my limit is either going to be what? Positive or negative infinity. And this one, we may have to test a number to determine which direction is headed. So if I have one family of function above another, and I'm approaching infinity, and I can tell which one is growing faster and slower, then your limit is either just going to be either 0 or plus or minus infinity. So that's a nice tool to have, especially if your function looks really messy. You're like, wait, what's going to happen here? So if we look at example 11 here, square root of 5,000x plus 100. Numerator falls under the category of what? Radical. Denominator falls under the category of a polynomial, algebraic, which is growing at a faster rate. Polynomial. Now, the 5,000x plus 100 initially is going to start off growing at a, it may start off at a further down the line than x squared, but eventually x squared is going to catch up and it's going to eventually overtake whatever large value radical has. And eventually this is going to get smaller and smaller. So my limit is simply what? 0. Yeah. Okay, 13. Again, this only works if we're approaching infinity. Okay, numerator, what family of functions does that fall under? Well, yep. Denominator is polynomial algebraic, which is growing at a faster rate. Algebraic polynomial, therefore my limit is still 0, right? Okay, approaching infinity, numerator, exponential, denominator, polynomial, which is growing at a faster rate, exponential. So this is either going to be what? Positive and infinity, and how do we decide between those two? That's 100 because we're headed towards in the positive direction, right? So plug in 100. If I plug in 100 in for x, my numerator will still be negative, and my denominator will be positive, therefore negative infinity. Right. Example 14. Numerator is radical. Denominator is logs, which is growing faster, radical. So it's either plus or minus infinity. What number can we test? 100. Numerator, we get negative. Denominator, we get positive. So negative 50. Sometimes students have asked, wait, what if the numerator was log plus polynomial, but then denominator was radical plus exponential, then which one is growing faster? You're not going to see a problem like that. Or, compared to the growth rates is for where it's easy for you to quickly make a conclusion. But if I have different families of functions paired up in numerator and a different family function denominator, then we don't want to use this strategy. We may use something called L'Hopital's rule down the line, but you're probably not going to see a problem like that. I think this is really helpful, more so with with these easy relationships that we can build. Right. Okay. Any questions? Hmm. Okay, let's start some of the review that I want to do with you here. So let me give you this review. Okay, let's see if we can put some things together. Oh, let's actually let me do this first. This is near the front of your previous packet. It says page 0 at the top here. Let me just kind of run through the big picture in terms of okay. When you're trying to, I think when we're looking at each individual strategy or type of problem, it's not too difficult. But when everything is mixed together, I think it's good to have a strategy in terms of, okay, this is what I'm going to do every time with this problem. This is what I'm going to do with this type of problem, so that you don't get lost in terms of, wait, what should I be doing with this type of problem? So let me just kind of highlight that there are two categories. Okay, so if we're evaluating a limit algebraically, there's two categories. The first category is approaching a real number, and the second category is approaching infinity. And we have different strategies for both. So if we're approaching a real number, the first thing we always do is what? Direct substitution, right? Ignore one-sided limit. Sometimes you're going to be tempted to be like, okay, maybe I should do decimals, as because there's a one-sided limit. Don't do that. Always plug in your x value. Okay? Always do direct substitution. And then you have three options that you can get. You're either going to get a real number, which if you do, then you end the problem. There's nothing more to do. Or you get indeterminate form, which is 0 over 0. Then that tells you that there's a limit that exists. And then we have those three sub-strategies, right? Where is it factoring that I got to cancel out? Is it conjugate method? We got to multiply by the conjugate to get the radicals go away. Or maybe we got to do a complex fraction common denominator to get the wholes to match up and pair up. Okay. And then the third option is if the limit does not exist. If it's like a vertical asymptote, like 10 over 0, 8 over 0. If that's the case, then limit does not exist. And then we say DNE. Unless it's a one-sided limit, then we have to look at decimals and then choose between positive and negative infinity. Okay. So if you see one-sided limit, don't jump into decimals too soon. Convince yourself that there's a vertical asymptote there before you do that. Okay. Let me just highlight a couple of things with zeros here. So let's say I find a limit and I get 0 over 4. What can I conclude? That's a real number, right? That's 0. And if I get 0 over 0, that tells me what? There's a hole, I keep going, but there is a limit that exists. We never want to say does not exist if we see 0 over 0. The point doesn't exist, but the limit does exist. And if we get like 10 over 0, then we know that there must be a what? Vertical asymptote. The limit does not exist. Unless it's a one-sided limit, then we got to go further, and then we may need to play with decimals. I want to make sure that if you get zeros that show up, make sure that you know what category they fall under, right? It's easy to look at zeros and assume one thing versus the other, but depending on where the zeros show up, it's either a real number, a whole, or vertical asymptote. We don't want to get thrown off between these three options. Now, if we're approaching infinity, then we have a different strategy, right? What we just went through, we compared degrees, right? We just treat it like a horizontal asymptote. And then your limit is either 0, ratio of the coefficients, or plus or minus infinity. All right. So let's look at page 1 here. Now, this is a piecewise function. So we have either different branches of graph, or we have order pairs all kind of spread out all across this graph, this function g of x, okay, made up of different points and lines and segments. So if we're approaching positive infinity or approaching 2 or 3 or whatever these numbers are, we have to first look at the restriction, figure out where on the graph we're looking at, and then we can pinpoint which expression to use to go through our evaluation. So it says limit as x approaches negative infinity. Okay. Which piecewise is that going to associate with? Negative infinity. First one, because negative infinity is less than 2, right? So it's going to be, we're going to follow this graph all the way towards negative infinity. So we're going to write it this way. Limit as x approaches negative infinity. Now, if we're doing infinity or negative infinity, what's our strategy? We're going to compare what? Compare degrees. Now, there's no denominator, so I can force the denominator to be what? X plus 5 over 1. Okay. All right, which degree is higher? Numerator, right? So I know this is either going to be, what are my two options? Positive or negative infinity, and now I can test what? Test the negative 100. Numerator, I get negative, denominator stays a 1, so negative or positive is negative, so negative 2. Okay, limit as x approaches 2 from the left of 2. That means which graph is slightly to the left of 2, leading up to 2. Yeah, first one. Okay. What's the first thing we do when we see limit approaching a real number? Direct substitution. Right. So what's our limit? 7. That's a real number. We stop, right? There's nothing more to do. We don't do decimals. There's no vertical asymptote here. Okay. Approaching 2 from the right. Right. It's slightly between 2 and 5. That's definitely to the right of 2, approaching 2. So 2x minus 1. What do we get? Great. Okay. Good so far? All right, careful with this one. Limit as x approaches 2 does not exist. Why is it not 11? Because, I mean, I see a 2 here. Why is it not 11? Good. This is a what? Yeah, order pair. This is a point. Remember, a point has no say with the limit, right? We're talking about the approach. Remember, in order for a limit to exist, the approach from both sides had to be in agreement. So this graph may look something like this, right? To the left is approaching 7. The other side is approaching 3. But then the order pair is all the way sitting up here at 11. If we want to find limit, we don't care about where that point is. We care about where the arrows are headed. And the arrows are headed in different locations. In order for a limit to exist, the one-sided limits have to agree. If they're not in agreement, we can say the limit here does not exist. That makes sense. Okay. Approaching 5 from the left. Which piecewise do we want to use? Middle one. Okay. Direct substitution. I get a real number, nothing more to do. Five from the right. That's this one here, slightly to the right of 5. Direct substitution, I get 9. Okay. What is the limit as x approaches 5? Good. Left and right are in agreement. The order pair is living elsewhere, but we don't care about the order pair. We care about how the graph is approaching. So, okay. Approaching 6 from the right. Last one, right? 6 is definitely in that interval from 5 to infinity. Direct substitution, we get 10, nothing more to do. Approaching infinity. Last one. We compare degrees. There's no degree below. I can force a 1 below. Degree 1 above, degree 0 below. Numerator has higher degree. We know this is either going to positive or negative infinity. So if I plug in 100, numerator is positive, denominator is still positive. So all right, let's do one more and then we can stop. Number 2. Use continuity conditions to justify whether a function is continuous or not continuous. If not continuous, identify type of discontinuity. So as a reminder, here are our continuity conditions. We need to commit these to memory. First condition, there's a point defined. Second condition, does limit exist? Sometimes we can get away with just writing limit statement once, but if it's a less than or greater than with 2 different functions, we have to explore a little deeper and actually do one-side limits. If the second condition fails, we stop and we say it's going to be a non-removable discontinuity. But the second condition passes, we always go to the third one. And the third condition, we're not pulling any new data. We're just looking at the first 2, what we gathered, and see if they're in agreement. If they're in agreement, great, all 3 conditions pass. My function is continuous at that point. But if the third condition fails, then we know it's going to be a removable discontinuity. The limit exists, but the point is not filling in that hole. So we have a hole in the graph. We have a hole discontinuity or a removable discontinuity at x equals c. Okay. All right, let's try number 2 here. Yes, question.
You have to say it's a jump this one here. Stop at non-removable.
Yeah, non-removable is fine. Okay, number 2. I want us to practice writing out our continuity conditions here. So first condition, does the point exist? What's our C value? 3, right? You're always going to be given some context clues where the focus of this problem is. So 3. All right, f of 3, which piecewise do we use? First one, 3 squared plus 5, 9 plus 5 is 14. We keep going. Second condition, does the limit exist? Do we need one limit statement or do we need 2? We need 2, right? We have 2 different functions split on either side of 3. So let's write it out. Limit as x approaches 3 from the left side of 3. Doesn't matter which one you do first. I'm just going to do the left first. And then separately, I'm going to write out limit as x approaches 3 from the right side of 3, and that is with the x squared plus 5. We do direct substitution for both. First one, I get 9 minus 2, which is 7. Second one, I get 3 squared plus 5, which is 14. What do you notice? They're not equal to each other. So the way that I want you to write it is I want you to say the limit as x approaches 3 from the left side of 3 of f of x does not equal to a limit as x approaches 3 from the right side of 3 of f of x. Therefore, the limit as x approaches 3 of f of x does not exist. And we can stop and say, what? What type of discontinuity? Non-removable. There's no need to look at the third condition if the second condition fails. But we're not doing discontinuity for the entire function. We're just proving discontinuity at what? At x equals 3. Okay, we'll continue with this review. I have another review packet for you that we can look at Monday and Tuesday, and then your test will be next Thursday. All right, come get your phones. Homework over the weekends. Check your calendar.
I just wanted to look that so I did a few conditions and then I said I'm not in agreement and that's what you first see any is that fine? Do I need to say this continuous add?
Yeah, you just have to make sure that we specified this continuity is at x equals 7, so just.
Okay, so I'm just.
That's the only thing. Yeah, everything's like.
Close to being.
I mean, I'll give you.
Good morning. Apologize for the interruption. Reminder at